Welcome you for this session on slope deflection method. In this session, we will be discussing on the application of slope deflection method to solve portal frames with sway. I'm taking this numerical example wherein we have a portal frame, which you can see here. We are required to solve by slope deflection method and draw its bending moment diagram. You can say it as a sway frame because of two things. One is we have the change in length of the vertical members, and there is also change in the cross-sectional properties of or stiffness of member AB and CD, wherein it is mentioned that for member AB it is I, moment of inertia, and for CD it is 2I. And we do get this sway analysis when there is an asymmetrical load which is acting on the member, and also when there is a horizontal load which is acting on the member. We will be considering it as a sway frame as we have discussed in the previous session. Now, in order to solve this problem, we will be considering the sway of an amount delta, by neglecting the axial deformation of the member, and we'll assume that this delta is same for both the columns. Okay. uh, this amount of delta, what is the value of delta, needs to be calculated, which is an unknown value. And we can see that as this member is getting deformed like this, there is a moment which gets generated at this joint, because in order to make this rotation zero over here, and here also there is a moment which gets generated here like this, and at joint D we'll get a moment like this. This is A, B, C, and D, and these are the moments because of sway. Okay. Now, because of which whatever moments which gets generated because of the sway, you can say that it is in the anti-clockwise direction. So this minus delta value is taken as positive, because we need to retain this minus 3 delta by L as it is, which gets multiplied by 2 EI by L, which would going to be equal to 6 EI delta by L square, minus 6 EI by delta by L square. These are the moments which are getting generated because of the sway of by an amount delta. Now here the delta is also an unknown parameter which needs to be calculated at a later stage. Now we'll proceed with the problem in a similar way how we have done non-sway frames and continuous beams, and let us see how this additional unknown parameter can be calculated. Now, calculating the fixed end moments, you can see, looking at the problem, we can say that member AB and member CD is not loaded. The member loading on these members are zero. So you can directly write that fixed end moments for these members MFAB, MFBA, MFCD, MFDC are equal to zero. And MFBC and MFCB will be going to be equal to WL square by 12, as it is loaded by a uniformly distributed load, which would going to be equal to minus 120 kilonewton meter, and MFCB would going to be plus 120 kilonewton meter. Now, by applying the slope deflection equation, we can say that MAB is equal to MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L, and we will be taking delta is equal to a positive value, and delta is an unknown value which needs to be calculated. And theta A, we will be substituting it as 0, as we have end A is fixed and even end D is also fixed. So theta A and theta D are 0. So I can substitute theta A equals to 0, and also we can write theta D is also equal to 0. And fixed end moment is also 0. We will get on simplification MAB is equal to 0.5 EI theta B minus 0.375 EI delta. So we have two unknowns in this equation. Similarly, I can write MBA is equal to EI theta B minus 0.37 EI delta. We'll apply slope deflection equation for span BC, and substituting MFBC as minus 120 plus 2E into I value for the horizontal member is 2I, so divided by 6, into 2 theta b plus theta c. And you can see that sway is only for the vertical members. The delta will come into picture only for member AB and for member CD. For the member BC, there won't be any sway. It is getting shifted, but there is no differential elevation for the member, because of which the delta would going to be equal to 0. So we'll have only the delta value for MAB and MBA calculation, and we will be calculating using delta value for MCD and MTC as well. Now MBC is equal to, on simplification we'll get it as 120 plus 0.667 EI theta B plus 1.33 into EI theta C. MCD is equal to MFCD plus 2EI by L into 2 theta C plus theta D minus 3 delta by L. Again, we'll substitute theta D is equal to 0 and EI of that member is 2EI. On substitution and simplification, we'll get it as MCD as 1.33 in EI theta C minus 0.333 EI delta. And we can similarly, on the basis, we can calculate MDC is equal to 0.667 EI theta C minus 0.33 EI delta. So we have now calculated all the end moments equations, MAB, MBA, MCB, MCD, MTC. We have three unknown values. One is theta B. Since theta A is equal to 0, theta B we have, theta C we have, and we have one more equation called delta. So we have three unknowns. So we need three equations in order to solve these three unknowns. But looking at the problem, we can say that we can apply joint equilibrium condition at B. That is, the summation of moment at B equal to 0. You can say that MBA plus MBC should be equal to 0. And similarly, I can apply a joint equilibrium condition at C, where MCB and M plus MCD should be equal to 0. I can generate two equations, but I have three unknowns. So we have to look for an additional equation. Let us see how this additional equation can be generated. Let us apply this joint equilibrium condition at B, which, as I said, it is a summation of moment about B equal to 0. MBA plus MBC is equal to 0. On substituting MBA and MBC, we'll get this equation 2.333 EI theta B plus 0.667 EI theta C minus 0.375 EI delta is equal to 120. And now we are calling this equation as 1. Similarly, we'll apply joint equilibrium at C, so that summation of moment at C equal to 0, MCB and MCD, summation of these two are equal to 0. Substituting the value of MCB and MCD, we get 0.667 EI theta B plus 2.667 EI theta C minus 0.333 EI delta is equal to minus 120. So we are calling this as equation 2. Now, in order to get a third equation, what we'll do is we will write the free body diagram of the column. If I draw the free body diagram of the column, we will have end moments at each end of the column. At end A, we'll have MAB, and at B, we'll have MBA. And similarly, for C, we'll have MCD and MDC. You can see here, I've taken all the moments in the clockwise direction. And since joint A is fixed and joint D is also fixed, there will be a horizontal reaction which would be acting at both the supports. And I will consider the direction to be in the positive direction. Now, I'm not worried about the vertical reaction because we are not considering any vertical forces as of now. So what I'll do is I'll consider only the horizontal forces, and I'll be considering the horizontal equilibrium of the frame in order to generate the third equation. Now what I'll do is, for this free body diagram, I'll apply summation of moment about B equal to 0 and summation of moment about C equal to 0, so that I'll be in a position to write an expression for horizontal reaction at A and horizontal reaction at D. Now if I apply summation of moment about B equal to 0, HA would going to be equal to summation of these two moments divided by the length of the member. MAB plus MBA divided by 4. Similarly, HD, the horizontal reaction at D, would going to be equal to the summation of these two moments, MCD plus MDC, divided by the length of the member, which is 6 meter. So now we have got an expression for the horizontal reaction at A and horizontal reaction at D. Now, if I look at the frame, we do not have any horizontal forces which are acting on the frame, because of which I can say the horizontal equilibrium as HA plus HD should be equal to 0. If suppose if there are horizontal forces, we have to consider that horizontal forces instead of 0. So we have to take the summation of horizontal forces to be equal to 0. In this case, we do not have any horizontal forces acting on the frame, because of which we are taking it as 0. Now I'll substitute what is HA. HA is MAB plus MBA by 4 plus HD is MCD plus MDC by 6 is equal to 0. Now we have different equations for this MAB, MBA, MCD and MDC that can be substituted, and we can simplify, and I will be in a position to get another equation which will help in the solving the unknown parameters. Now on simplification, we get this equation as 4.5 EI theta B plus 4 into EI theta C minus 3.583 EI delta S equal to 0. This is third equation which we are generating. So now as we have three equations with three unknowns, these three simultaneous equations we can solve and get the values of three unknowns. So on solving, we get EI delta is equal to 23.842. So it is a positive value that the sway is happening in the positive x-axis. EI theta B is equal to 72.43 in the clockwise rotation. EI theta C is minus 60.127. It indicates that it is in the anti-clockwise rotation. So once I know these rotations, I will be in a position to substitute those values of theta B, theta C and delta in the equation of slope deflection. We will be in a position to get the values of MAB, MBA, MBC, MCB, MCD and MDC. All the end moments can be calculated by knowing these values of EI theta B, EI delta and EI theta C. So on substitution, we'll get the end moments as MAB is equal to 27.274, MBA is equal to 63.49, MBC is also equal to 63.49, MCB is equal to 80, it should be equal to minus 63, and MCB is equal to 88.16, and MCD should be equal to minus 88.16, and MDC is equal to minus 48.04. So these two are equal and opposite, and these two moments are equal and opposite. Now with these values of bending moment, end moments, we can write the bending moment diagram, and we can superimpose the simple bending moment to get the net bending moment diagram. So we can see that there are no vertical members are not loaded with member loading, because of which we do not have any simple bending moment. We can see there is a uniformly distributed load, which we can calculate what is the magnitude of which works out to be SW L square by 8. For that loading, we'll get it as 180 kilonewton meter. So now on the whole, in a sway problem, we will be calculating considering a sway of delta, and that also becomes an unknown parameter. In order to get the additional equation to calculate the value of delta, this is a step which we will be performing compared to a non-sway frame, wherein we'll consider the free body diagram of the vertical members, and we consider the horizontal reaction and the end moments, with which we will be in a position to write an equation for horizontal reaction by taking moment about B and C equal to 0. Once we do that, we will going to write a horizontal equilibrium of the whole frame, considering all the horizontal forces which are acting on the frame, with which we will be in a position to develop an additional equation which helps us in solving additional unknown value delta. So with this, we this session. We have completed almost all the types of problems we can solve through slope deflection method. Thank you.